Hello chemists, this is Miss Placino and you are watching Screencast 6.2 on the mole and molar mass. Today we're going to talk about what the mole is and how it relates to the mass of a substance. The mole is a unit that you might not have come across just yet. It's something that we as chemists get really excited about because it allows us to connect a bunch of units that wouldn't be related otherwise. So this is going to be a really important unit, not just for this topic that we're currently studying, but really for chemistry in general. Let's take a look at the do now. Make a list of words you know that pertain to specific numbers. So pause the video, give it a shot. I've gone ahead and brainstormed 6 different words I know that pertain to specific numbers. Maybe you came up with some of the same, maybe you've got some different ones. Not a big deal either way. So dozen is one. You know, you have 12 things, whether it's people or donuts or whatever, you've got a dozen. A baker's dozen represents 13 things, the usual dozen, plus 1 for the baker. A duet, that usually is associated with the number 2. Trio, 3. Gross, you might not know this one, it's 144. Quartet, 4. There are other ones out there, of course, and it turns out that the mole is one of these words that relates or pertains to a very specific number. So let's get into a little bit more information about that. So when we say the mole in chemistry, we're not talking about this mole. We're also not talking about this mole. I guess it's kind of cute. This is a mole that lives underground. It's pretty much blind, and hopefully you can tell from its claws it does a whole lot of digging. Chemists aren't really interested in that mole either. We care about the SI unit of quantity. It's also called Avogadro's number. So just like when you think of the word dozen, you think 12. When you think of mole, you should think of this number, 6.022 times 10 to the 23rd. That is a gigantic number. It is a dozen on some very serious steroids. But it's the same general idea. A dozen always means 12, regardless of what you're talking about. Eggs, bagels, donuts, people. A mole always is talking about 6.022 times 10 to the 23rd. Often you'll see us just round it to 6.02 times 10 to the 23rd. Either way is fine with me. This number is usually reserved for just counting the number of molecules or the number of atoms in a given sample. We need this huge number if we're talking about something as small as an atom or a molecule. We don't usually use the mole to describe much of anything else. All right, a seemingly unrelated question, but we'll connect it all back together, I promise. How could you determine the number of jelly beans in the jar? Come up with as many different techniques as possible. And yes, you are allowed to open the jar. You can take the jelly beans out. You can't eat them. So see if you can come up with some different ways, and we'll talk in a minute. So one thing you could probably do is just simply open up the jar of jelly beans, dump them out, and count them. You could ask a freshman to do this. They're really good at stuff like that. So that's probably the simplest way to go ahead and figure out how many jelly beans are in that jar. Another way you could do it is by weighing. You could take the mass of one jelly bean, and then you could take the mass of all the jelly beans that are in the jar, and then you could just divide the total mass by the mass of a single jelly bean and hopefully come up with a whole number so that you can figure out the total number of beans in that jar. Another technique that you might be able to use is volume. You could find the volume or the space occupied by a single jelly bean. You could find the volume of the jar itself. And again, just do a simple division, total volume divided by volume of a jelly bean, and hopefully figure out the number of jelly beans in the jar that way. There are some methods that are more practical than others. Finding the volume of a jelly bean might be a little bit difficult. They're probably not perfectly packed together, but there's some open spaces. So this might not be the best option given what we're working with. Counting, if you're talking about a relatively small jar, isn't too bad. You can imagine as that jar gets larger and larger and you have more and more jelly beans to count, no one really wants to do it this way. It's tedious and you're prone to making errors. Weighing it might be one of the best ways or the best way to take care of it. And it turns out when chemists are trying to count atoms, we like to do it by weighing too. Of course, it's impossible for us to go in and see the individual atoms and molecules so that we can count them. Plus, they're just going to be way too great in number. Think about how big the mole is, 6.02 times 10 to the 23rd. It would take you your entire lifetime many times over to count up to a mole. So it's most practical for chemists to count by weighing. Let's talk a little bit about how we're going to do that. So we've got something called formula mass, which is also known as atomic mass. They're one and the same. And all that is the sum of the average atomic masses of all the atoms in a substance. And we measure it in U. We can also use AMU. I'm not particular. You might remember that unified mass units or atomic mass units are what we use to measure the mass of subatomic particles. Also, we use it to measure the mass of individual atoms. We can use it to find the mass of a molecule. So let's say you've got one water molecule and you put it on an impossibly small scale and you find its mass is 18.02 U. If you break it down, a water molecule consists of 2 hydrogen atoms and 1 oxygen atom. And you can use the periodic table to find that a hydrogen atom has a mass of about 1.01 U. There are 2 of them, so we have 2 times 1.01 U. The oxygen atom, there's just one of those, and it's got a molar mass of 16.00 U. So when I do that simple math and I add it up, I come up with a mass of one single water molecule being 18.02 U. Let's have you try some out. Just in case you're a little confused, I'm going to walk through, we'll do 1 and 2 together. So basically I take the subscript of the element, in this case 2 for nitrogen. I'm going to multiply it by the atomic mass that I find on the periodic table. Then I'm going to add that to, in this case, I've got 5 oxygen atoms. Each of them have an atomic mass of 16 atomic mass units. And that's really it. Hopefully this is very straightforward math. You come up with 108 U. A lot of the elements are pretty close to whole numbers. I'd say if you've got a decimal point place of 0.2 or less, feel free to just round down. If you're at 0.8 or higher, feel free to round up. If you're somewhere in between, don't just round to the nearest whole number. Let's do an example. Calcium has about 40 U plus 2 chlorines, each with a mass of, the reference table tells us 35.45. We don't need to be quite that specific, but I wouldn't want to really round up or round down from there. So let's call it 35.5, oops, forgot my unit, U. When I add those up, I get 111 U. Why don't you pause the video and try these other 6 on your own. You can check your work against what we've got on the screen. If you're off by like 1 atomic mass unit, maybe you just rounded a little differently than I did. If you've got something carried out to the 10th place, I've just rounded to the nearest whole number. As long as you are reasonably close, you're in good shape. And this is something on a quiz or a test. I don't need you to show me your work here. I trust that you can multiply and add in your calculator, if not in your head. It's very, very rare, if not completely impossible, for us to work with a single molecule or a single atom at a time. Molecules are extremely small, so it's impractical to look at just one at a time. We're going to be looking at moles of molecules. Instead of using formula mass or atomic mass, looking at the mass of one single molecule, chemists like to use molar mass. This is the mass of 1 mole of a pure substance, and we measure this in grams per mole. Now, a lot of times people think that this is going to involve extra calculations. We know that there are 6.02 times 10 to the 23rd things in a mole. So if I have a whole mole of molecules, that must mean that I've got to do a lot of math to figure out its mass. Fortunately, people who think that are completely wrong. Everybody tries to do it that way. Well, maybe not everybody. Lots of people try to do it that way, but it's so much simpler. Let's go back to our water molecule, H2O. If I have a mole of water molecules, it has a molar mass of 18.02 grams. hopefully this number is looking really familiar. If you look back at your notes, 18.02 U was the mass of one single water molecule, and now I have a whole mole of them, and they have a mass of 18.02 grams. It's the same exact math. The only thing that changes are the units. So we're looking at, instead of just 2 atoms of hydrogen and 1 atom of oxygen, we're talking about moles. 2 moles of hydrogen, 1 mole of oxygen gives us 1 mole of water molecules. But my math doesn't change. I've got my molar mass of hydrogen at 1.01 grams per mole times 2, since H2O. I've got 1 mole of oxygen atoms at 16.00 grams per mole. And when I add those up, I get right back to that same number, 18.02, except now my units are grams per mole. This is huge for chemists. Working in grams is much more useful than working in atomic mass units. So now we found a way to connect a counting number to mass. So this is really powerful stuff. In the previous lesson, we were talking about using dimensional analysis to convert between units. The big application for dimensional analysis is with the mole for this unit. So I know that 6.02 or 6.022 times 10 to the 23rd things, again, usually atoms or molecules, but just in general, anything is going to be equal to 1 mole. So you have this as a practice problem. Let's walk through it together. I have 0.862 moles of, this looks like dihydrogen carbonate, also known as carbonic acid when it's dissolved in water, and I want to know how many molecules are present in that sample. The same general rules that we talked about before will apply. Take the information you've been given and we rewrite it. Sometimes you just put that over 1 to keep things organized. I know that 1 mole is equal to 6.022 times 10 to the 23rd things. In this case, instead of items, I could substitute in molecules. In order to get the mole to cancel out, I want to put 1 mole in the denominator and 6.02 times 10 to the 23rd molecules in my numerator. Moles cancel. I can plug numbers into my calculator. Be careful entering your values in scientific notation. And you should come up with 5.19 times 10 to the 23rd molecules to the correct number of significant figures. I've got 3 sig figs in both of those values, so I should have 3 sig figs in the answer. Let's look at another practice problem. So we just take care of letter A. Let's check out letter B. This time we're told that we've got 4.25 times 10 to the 23rd atoms of cobalt, and we want to convert that into moles. So as usual, just start by rewriting the number you've been given along with the units. I have a whole bunch of atoms. I want to convert it into moles. So I'll put the unit I want up in the numerator. I can use 6.02 times 10 to the 23rd atoms in the denominator. That'll get atoms to cancel out, leave me with an answer in moles. And I come up with a final answer of 0.706 moles. So there are 4 practice problems remaining. I really recommend that you try these out. Make sure that you can do these basic mole conversions between atoms and molecules into moles. We're going to be building on this concept tomorrow when we talk about other types of conversions we can do with a mole, and ultimately putting them all together to solve different types of problems this unit. So make sure that you've got a strong foundation in this stuff and that you're capable of doing hopefully pretty simple problems like these. All right, that wraps it up for today. I hope you found this tutorial helpful, and thanks for tuning in.